Now if in the equation, just it is continued to last video, let's go. If here in this equation I0 equal to 1, if we put in this equation, what we get here, W equal to 1 by 2 L into I0 square is the equation. If you put I0 equal to 1, I0 square, again it comes to be 1. What we get, W equal to 1 by 2 L. This can be written as, move this 2 to this side, twice W equal to L, and from this twice W equal to L we get another definition of this, nothing but what, self induction, the twice W equal to L or L equal to twice W. The definition we can just given in your book, I will read it. Self induction of a circuit is numerically equal to, twice the work done in establishing the magnetic field or magnetic flux associated with a unit current in a circuit. If unit amount of current is passing through the circuit, how much work done is required to establish the magnetic flux? Twice of that is nothing but a self-induction. Same thing they have given in your book. Now if you compare this equation, just I will write the two equations again. So if you compare this one, W equal to 1 by 2 L I0 square, this is nothing but what, work done, and this work done itself is stored in the form of energy. So we can write this as equal to energy. Just I will write here. Same equation can be written as, this work done itself can be stored in the form of energy. So we can write this equation as E equal to work done equal to 1 by 2 L I0 square. So this is the energy, but we know in general the kinetic energy can be written as 1 by 2 m into v square. 1 by 2 m into v square is nothing but our equation for kinetic energy. Here it is current square, here it is voltage square. 1 by 2 is there, here also the 1 by 2. Then what is the function of L here? If we see in both the formula, here it is L now and here it comes to be mass. So the L means self-induction play the same role as that was played by the mass. Self-induction L play the role same as that of the mass. From these two equations, if we equate them, that we can understand. Let's go to for next topic, inductance of solenoid. Suppose we have the solenoid and we want to find the induction of that solenoid. How can we find out? Induction of solenoid. So I will write here an induction of solenoid. So first of all of you need to know what exactly solenoid means. Solenoid means what? It is nothing but a one insulating cylinder like this. Such type of cylindrical part they have taken. It is said to be cylindrical insulator they will take, and just they will take a wire, conducting wire, and wound it on this like this. So 2 turn, 3 turn, 4 turn, 5 turn, 6 turn, 7 turn. So current passes from one end, current leaves from other end. So this resultant thing is said to be solenoid. And when current passes from this coil, what will occur according to Faraday Law? EMF is induced, and due to that EMF induced, current get induced and it will produce as a magnetic field exactly in opposite direction. It will oppose. Now suppose this is the axis of this solenoid, then at the center or axis of solenoid, how much magnetic field is produced? That already we know. At this center, magnetic field produced B equal to mu 0 n into I. Mu 0 n into I, where I is current passing, I is a induced current in the circuit. Now we have to derive this. This is nothing but solenoid. I hope all of you get idea about solenoid. So this is magnetic field produced at the center. Now here, as we know, what is the value of magnetic induction? What is the value of self-induction? Just we have derived L equal to N is the number of turn into phi magnetic flux. Capital N is the number of turn. Phi B is a magnetic flux. Phi suffix B is a magnetic flux. So N phi B divided by I is a induced current. That will give the self-induction that already we have learned. If you have a book, in your book equation 12.28 is there. Same equation I have written here. So that formula already we know. But here, as we know, this magnetic flux can be written as number of turns As we have taken capital N is a number of turns, the same equation little bit can be written in different form as N phi B, N into phi B, number of turns into magnetic flux, that is equal to NL small nl into B magnetic flux dot area A, their dot product. It is a vector quantities. N into phi B equal to NL into B dot A. What is N? Number of turns per unit length. Number of turns per unit length. L is a length of this solenoid. L is a length of this solenoid, and we can write for this solenoid number of turns capital N equal to number of turns capital N divided by length of solenoid. Number of turns capital N divided by length of solenoid. It is said to be number of turns per unit length small n, that we have taken here. So what we have done, N phi B equal to N into L. From this you can find the value of capital N. So capital N equal to NL. So same thing they have done here. As we know, the formula is N phi B equal to B dot area A. But here number of terms are N. You should take N here. But instead of N, we have written here NL. From this formula, we have kept it here. We get this equation. And here, if we solve it further, it comes to be NLBA. NLBA, because angle between them is 0. If angle between them is 0, we can write this like this. So cos 0 is 1. So NLBA, that equation we get for theta equal to 0. Now we can write the same equation for this self induction. You can put this value and you can write this. So N phi B we have derived is this value we have to kept here. What we get, I will write further. So N phi B is what? NLBA divided by I. So it is NL into B into A divided by this I as it is. So we get this equation NLBA divided by I. We have put the N phi B from this equation to this equation. We get this equation like this. NLBA divided by I. But what is the value of B? This B at the center of the coil, that was given by this equation. Put this value of B in the equation and rewrite the equation again. So I will just erase the bottom part and will solve it further. So just put the value of B from this equation to this and rewrite. So L equal to NL mu 0 Ni into A divided by I. This I get cancelled with this I. So what we get? We can write mu 0 N square LA. Mu 0 N square LA. We get mu 0 N square LA. That is nothing but a self-induction L equal to that we have derived by this formula, and we get this equation L equal to mu 0 N square LA. After that, if we know the A is the area of the solenoid, we can put that value and we can write this as mu 0 into N square into L is the length. Now area is what? Area is what? Area is nothing but a pi r square divided by 4. Area of the cylinder, pi r square divided by 4. So pi into d square divided by 4. Pi into d square divided by 4. So d is nothing but a radius of this solenoid, pi d square divided by 4. So d is the diameter of this solenoid, so pi d square divided by 4 is nothing but a self-induction we have find out. If we move this L from this side to this side, what we get? The self-induction per unit length. Then this L will be not there, and this equation we get self-induction per unit length as same thing that they have mentioned in their book as equation 12.34. From this equation we can say L is directly proportional to mu 0. L is directly proportional to N square, number of turns per unit length, its square. L is directly proportional to length. L is directly proportional to area. And that is in terms of this equation, L is directly proportional to square of diameter. square of number of turns per unit length and directly proportional to mu 0. So this is nothing but what? Inductance of solenoid that we have derived here. Now if there are large number of inductors connected in the circuit, if there are large number of inductors connected in a circuit, either in series or in parallel. If you remember, in 11th standard we have learned resistors in series, resistors in parallel. Similarly, we have learned capacitors in series, capacitors in parallel. Same way, if there are inductors large in number, if three inductors are there, they are connected like this. Suppose this is the first inductor, second inductor, and third inductor. So this is the L1 suppose, this is L2 suppose, it is L3 suppose. Three inductors are connected like this, one after other in the form of chain, then they are said to be connected in series. In this case, resultant inductance of the circuit is a sum of inductance of each L1 plus L2 plus L3 as for series. So this is the formula for series combination of resistor, which is this. Instead of this, if the coils are connected such that they are connected in parallel to each other like this, suppose the three coils we have, they are connected like this, their other ends are made common and then they are connected in the circuit like this. Then they have connected the circuit, this is L1, this is L2, L3. Then these three resistors in this diagram are said to be connected in parallel. Then the resultant inductance is nothing but a LP. S for series, P for parallel. So when they are connected in parallel, LP equal to can be written as 1 divided by LP equal to 1 divided by L1 plus 1 divided by L2 plus 1 divided by L3. If the three resistors are there, these are the formula for series, these are the formula for parallel. If n number of inductors are connected, then this plus so on up to plus Ln. Add all the inductor in series. In parallel, add all their reciprocals in parallel, plus so on up to plus 1 divided by Ln. So this is nothing but what? Series combination. This is nothing but a parallel combination of inductor. And how to find the resultant inductor in series? Just by adding an individual inductor's value. In parallel, just adding the reciprocal of them, and then we get a total inductance of a circuit. So this part is little bit similar to the resistors, exactly similar to the resistors in series and resistors in parallel, little bit opposite to capacitors in series and capacitor in parallel. Now we have to learn energy stored in magnetic field. Energy stored in magnetic field. If you remember, we have learned energy stored in capacitor. If you remember, in electrostatics we have learned energy stored in capacitor. By the same way, we have to find out energy stored in inductor in magnetic field. Energy stored in a magnetic field. Energy stored in magnetic field. Not inductor, energy stored in magnetic field, that we have to derive similar to energy stored in electric field. So if you remember, energy stored in electric field can be written as U suffix E equal to, if you remember electrostatics we have learned, it is Q square divided by twice C, where Q is a charge, Q is a charge, C is a capacitance of capacitor, Q square divided by twice C. If you solve it further, we get CV square C into V square divided by 2, or it is said to be 1 by 2 CV square. If you solve, if you put the value of Q equal to C into V, if you put C into V, C square V square, 1 C cancel with the denominator C, so CV square by 2, it is said to be 1 by 2 CV square. It is said to be 1 by 2 CV square. This is nothing but what? This thing already we have learned, energy stored in a capacitor. Now we want to just find out the same type of energy stored in a magnetic field. How the energy gets stored in terms of induced EMF, induced current and induced magnetic flux. It will store some part of energy in an inductor. How inductor, or we can say coil, that will be energy will be stored in terms of changing magnetic field. How it gets stored? As we know, according to Faraday's law, as E equal to minus L into di by dt. If you remember, just before we have derived this equation in terms of a inductor. Now the work done in moving a charge dq against this EMF, if this EMF is produced in a coil. Now suppose I want to move the charge dq by small amount. I want to move the charge dq in this EMF. We have to apply some work, and that work done can be find out W equal to EMF induced with a negative sign into charge to be moved. I want to move the dq charge in the presence of this EMF, then the work done is required. That work done is minus E into dq. Now put the value of E here and we can solve it further. So this minus and this minus become a plus. So we can write L into di by dt, in the self induction into di by dt into dq. dq is a charge to be moved. Now same equation can just move this dt to this side. We can write this as L, I will write here L into di into dq divided by dt. Rate of change, flow of charge per unit time is a current. So we can write further L into, this is I into di. I into di, that is the work done. dw should write for a charge dq, the work done is dw. So we get this dw equal to L into I into di. This is a work done to move the charge, small charge dq. I want to find total work done to move all charges. We have to integrate this equation where current varies from I to I0. We get work done equal to what? L into I square divided by 2. The limit varies from 0 to I0. This part already we have solved initially. If you put upper limit minus lower limit, what we get is equal to 1 by 2 L into I0 square. That is a work done. W equal to 1 by 2 L into I0 square, or it is said to be I square. If we have not put the limit, if we have put instead of I0, if you put here I, then this becomes 1 by 2 Li square. This much amount of work done we have to perform to overcome a magnetic field due to this EMF. And this work done itself will be stored in the form of energy stored in a magnetic field, and that was represented by U suffix B. Energy stored in a magnetic field, that is nothing but a work done, that is 1 by 2 Li square. If we solve it further, we can modify the equation to B square divided by twice mu 0 as they have mentioned in your book. Try to find out that equation. That will be homework to all of you. So this is nothing but what? The energy stored in a magnetic field that we have learned today. So this much part is sufficient today. In next period, we will see the mutual induction. I think we should start mutual induction a little bit. So we are not going to stop here. We start a mutual induction. So this much energy stored in magnetic field in the coil in terms of changing magnetic field. Now we have to start a new topic of the same chapter, that is said to be mutual induction. Mutual induction. What exactly this mutual induction, that we have to see. If you remember, initially we have seen the self induction. Now it is said to be mutual induction. Self induction is nothing but what? Due to current flowing to the same coil, in the same coil EMF is induced. That is said to be principle of self induction. Now instead of that, we have the two coils. Suppose we have the two coils. I will draw it here. Suppose this is the first coil we have, okay, and this is second coil we have. The two coils we have like this. Now here to the first coil, the variable resistance is applied, the battery is applied, and one key is applied. So this is plus minus, this is a battery eliminator E, this is a key, this is a resistance variable, it is said to be rheostat. And to the other coil we have attached to the galvanometer only. So this coil we have attached this as a galvanometer. Now when we close the key from this, current will flow from positive to negative. So this is direction of flow of current. Current flows, what will occur? It will produce a magnetic field or EMF in the same coil is induced according to Faraday's law. That EMF induced is linked with the secondary coil like this. Such type of diagram they have drawn. And if that EMF is linked to secondary coil, galvanometer shows a deflection. When we close the key, current passes to the first coil, it is changing, it will link with the secondary coil, it will induce the EMF in secondary coil, and this phenomenon of production of or induction of EMF in a second coil due to flow of current in first coil is said to be mutual induction. Principle of mutual induction. The phenomenon of production of EMF in second coil due to flow of current in first coil is said to be phenomenon of mutual induction, and the first coil which is connected to battery eliminator is said to be primary coil, and the second coil which is connected to galvanometer, it is said to be secondary coil. So these are the primary coil and the secondary coil. So what is the phenomenon? Current pass from the first coil, it will induce a EMF in a second coil. This phenomenon is said to be principle of mutual induction. If we apply this eliminator here and pass a current to the secondary, definitely in the first coil the EMF get induced, and that is nothing but a phenomenon of mutual induction. Phenomenon of mutual induction. Now in this case, suppose we have seen this current flowing to the first coil is I1. I1 amount of current is flowing to the first coil, and it has a magnet. It will produce a magnetic field here. It is a B1. B1 is a magnetic field produced by the first coil. I1 is a current flowing to the first coil. Then what will occur? It will induce a magnetic flux. This magnetic field produced by the first coil due to this current, that is linked to the secondary coil, and that is said to be phi 1 2 or 2 1. They have taken 2 1, phi 2 1. Due to this current, this magnetic field is produced. Due to this magnetic field, this phi 2 1 is the amount of magnetic flux linked to the secondary coil. So phi 2 1 stands for what? Current flowing to the first coil induce a magnetic field in second coil. Just come in this direction. So like this I will write phi 2 1, come like this. Current in first induces a EMF in second. Phi 1 current flowing from first coil produce a magnetic flux in second, 1 to 2, like this. So that is nothing but a part that we have learned. So here phi 2 1 is a magnetic flux produced in a secondary coil. Now we want to find out that magnetic flux linked to the secondary coil. That can be found out by formula. Here I will write phi 2 1 equal to magnetic flux produced in secondary coil due to a flow of current in a first coil. That can be found out by one formula. That formula we can write phi 2 1 is directly proportional to current I1. If current changes more magnetic field change. More flux is linked with the secondary coil. So thus phi 2 1 magnetic flux linked to the secondary coil due to flow of current in first coil directly proportional to current flowing to the first coil. Now we can just remove the proportionality sign. You can write phi 2 1 equal to some constant m into current flowing to the same coil, and the constant m with the suffix same as this 2 1. Then this m21 is said to be coefficient of coefficient of mutual induction, or simply said to be mutual induction. So phi 2 1 equal to m21 into I1, that we get here. Here this is nothing but the equation we have derived. So phi 2 1 equal to m21 into I1. This phenomenon is said to be principle of mutual induction. Now we know, according to this Faraday's law, we can write the same equation in terms of Faraday's law we can use. What is the Faraday's law for this? Just I will write a little bit here. E equal to, just I will write here, E equal to, E is nothing but what? EMF induced in secondary coil due to flow of current in first coil. So it is again E21. Again E21 equal to what? Minus d phi 2 minus d phi by dt. That is the formula, but phi here it is 2 1. So it is d phi 2 1 divided by dt. Put the value of d phi 2 1, that is nothing but this one. We can write E equal to E21 equal to, just this value we have to keep here, minus M21 into di1 by dt. Minus M21 into di1 by dt. So this is nothing but what? EMF linked to the secondary coil due to flow of current I1 in the first coil. This is a magnetic flux linked to the secondary coil due to current I1 flowing to the first coil. So this we have derived, that is EMF induced in secondary, due to flow of current in primary, the magnetic flux linked with the secondary due to flow of current in a primary, that we have learned. Suppose we have changed the direction. Suppose this galvanometer is connected here and this whole thing goes here. Whole thing means resistance, eliminator and key is connected to secondary coil, galvanometer moves to the primary coil. Then in that case what we can write similar to this, just I will write little bit aside. This equation we are going to write in that case. This part is moved here, this part comes here. So instead of 521 what we get, 512 is directly proportional to I2. 512 is then what? Magnetic flux produced in a first coil due to flow of current in a secondary coil, and secondary coil current flowing is I2. Here it is I1, here it will be I2. Now 512, instead of this B2 goes here, here it is I2, B2, I2. Here what is that? Magnetic field flux B, instead of B1 now what is 512 will come. So 512 is directly proportional to this. Remove the proportionality sign. 512 equal to M12 into I2. By this method we have find out this, we get this equation. Again apply like this, just apply the Faraday's law to this and solve it further. So we can write E12, EMF produced in first coil due to flow of current in secondary coil, is equal to minus D 512 divided by dt. If we solve it further, it comes to be minus M12, put this value here, minus M12 di2 divided by dt, that is nothing but a E12. So we have derived this equation. Just initially we have derived this and this equation. Similarly, now we have derived this equation and this equation if we change the position of battery eliminator and galvanometer. Just move this part here, move this part here. In general, what we can write? In general, we can write a simple thing for this. If the current through the primary changes, it will produce an EMF in secondary. This is the first coil, primary coil, secondary coil, second coil is secondary coil. Suppose I1, I2 we have replaced. Current from a primary is EIP. Current from a secondary if we put as a IS. Current from a primary if we take IP. So this is current from a primary coil, IP. Current from a secondary coil, it is IS. EMF linked to the first coil, it is EP. And here it is ES. EMF in the secondary coil. If this sign conventions, if you give in general, what is this mutual induction? M equal to, just find out, M equal to 5 divided by I1. 5 divided by I1. Here it is primary coil, so magnetic flux is 5P. Secondary coil, magnetic flux is 5S. Secondary coil, magnetic flux is 5S. It is 5P, here it is 5S. In general, we can write M equal to magnetic flux divided by current. Magnetic flux divided by current. Now, magnetic flux divided by current means what? Flux through the secondary. Flux created secondary due to flow of current through the primary. So 5S divided by 5P. Such type of equation we can derive. And in general, this M12 and M21 both are same. M12 equal to M21 equal to M. M12 equal to M21 equal to M. Both are same in magnitude. So this is nothing but what? Concept of mutual inductions we have learned up till now. Now we have to go to the definition of this. Definition of the mutual induction we have to learn similar to as we have learned in a self induction. So what we can say, just I will write directly the equations now. 521 equal to current in a first coil induce EMF in secondary coil is equal to what? M21 into I1, and 512 equal to M12 into I2. This type of things we have learned. This type of thing just we have derived before. Okay, so from this you can find the value of M M21 equal to M12. I have told you both are same, and that is nothing but M equal to what? Phi 21 divided by I1 is equal to what? Phi 12 divided by I2. Just use this. What is M12? Phi 21 divided by I1. M12 Phi 12 divided by I2. So that thing just written like this. Now in general, what is this? Just we have seen before also. So in general we can write M equal to phi divided by I. Phi divided by I. If current flowing through the primary coil, it will induce an EMF in secondary coil. Phi s divided by phi p. Like this. Okay. From this just find the value of phi s here. So this equation implies phi s, magnetic flux linked to the secondary coil, M into IP we get. M into IP we get. Now just use the Faraday law. E equal to minus d phi by dt. So d phi by dt, and here it is secondary coil. So d phi s. Just put this value. What do we get? Minus M into primary coil dip divided by dt. M into dip divided by dt. From this find the value of M, mutual induction, equal to minus E divided by dip divided by dt. From this we can explain what is a mutual induction. Mutual induction is a ratio of EMF produced in a secondary coil to the secondary coil. So it's 5 years now, so we should take here it is ES. So it should be ES. So ES, EMF induced in secondary coil to the rate of flow of current in a primary coil with time. Their ratio is always constant. That is said to be mutual induction, represented by M. And we know that already this ES is measured in volt. This is measured in ampere per second. If we solve it, it comes to be ohm into second, and it is said to be Henry. It is said to be Henry. That already we have done. Ohm into second, that is said to be Henry. That means what? When a current of 1 ampere per second, when this current of 1 ampere per second pass through the primary coil, and it will produce a EMF of 1 volt in secondary coil, then we can say mutual induction is said to be 1 Henry. So this is nothing but things that we have to learn today. In next chapter, next topic, we'll see coefficient of coupling between two circuits or two coils, and then the last topic of this chapter we will see transformer. Then we'll stop here. So just watch this video. After watching this video, try to read the same topic from a book. It will increase your understanding. Then after reading from a book, again watch the same video. It will increase your concepts. Okay, so see you in the next video. Thank you. Bye.